And it can start with lead code. Okay, 5.71%. Problems, count of matches and tournaments. Easy. Okay, so you're given in DJN the number of teams in a tournament that has strange rules. If the current number of teams is even, each team gets paired with another team. A total of n by 2 matches are played and n by 2 teams advance to the next round. If the current number of teams is odd, one team randomly advances in the tournament and the race gets paired. A total of n minus 1 by 2 matches are played and n minus 1 by 2 plus 1 teams advance to the next round. Return the number of matches played in the tournament until the winner is decided. So there is a pattern. Let's see. Number of matches. Mm, mm, let's say seven, seven things. 3 on 3 will play. Number of matches. We have 3 plus 1, 2, 3. Okay. So we have like 2 things and this. Mm, okay. 7 matches. 7, 3, 2. After 3 hours, 2. Let's take 40. So 20 matches are played. So in 20 times are like 10 matches are played and 10 matches are played. So 20 out of 40 teams. So at 40 teams, 20 matches will be played and 20 teams advance to the next one. Now out of 20 teams, like 10 matches will be played. And 10 teams advance to the next one. So 5 matches for the next. Now 3, 2, 1 will be there no matter what. 7th year. Yes. No, 20, 10, 5. So we keep dividing by. Okay, so if the number is even, we'll add half of it. If the number is odd, we'll add half of it plus 1. Yes, that's it. Okay, so y n exists. So 10 1 by 2 equal to 0. So nth count matches equal to 0. So the number of like teams are even. So count matches in the if half like n divided by n else count matches plus equal to 1 plus n minus 1 equal to n in order to calculate this one. So the main vector that's equal to 5. It's return from
Hello. How good evening. हम्म, हम्म,
modification.
ओके। आप है कहाँ पर अभी?
This should be.
हाँ, मैं आऊँ क्या वहाँ पर अभी?
Okay, let's get
हाँ, वहाँ से बस कितना होगा? 1 किलोमीटर दूरी पर हूँ मैं।
one,
सुनिए ना, इधर ऑटो वगैरह मिलता नहीं है। आप आइए ना, मेरे रोड पर ही हूँ। आकांक्षा मोड़ से जैसे अंदर आते हैं ना, उसी रूट में।
one next time.
इको स्पेस तरफ, इको पार्क तरफ नहीं, इको स्पेस तरफ, अंदर अंदर पंप से जो रुक गया है ना। आइलैंड से मैं किधर होता हूँ? राइट तरफ। मैं लोकेशन भेज रहा हूँ। ठीक।
Okay, seven.
मैं जा रहा हूँ, मैं पंप से। ठीक
Who's that?
है, यही इसमें
मतलब ऑफिस आवर्स के बाद भी बुला रहा है मतलब इसका एक्स्ट्रा पैसे नहीं देगा।
मेन चीज है।
हाँ
मेन चीज है कि इतना मेरी सैलरी है ना, 2 घंटे में उतना पेट्रोल मिल जाता है। ठीक है, अगर एक दिन तो बंद पड़ा था ना,
ओके
तो कितना
बहुत लॉस
मुश्किल
है।
आ सकता है। ये हाई सेलिंग पेट्रोल पंप। ऐसा बिल्कुल।
One minute. Later, five. Oh, if like if it is even, if you check this lamp, if one is even, let's say for 10, then the next number of teams will be like, yeah, if I it may do. And if like let's say I'm equal to 11, so it should be like 6. It looks like this. If you can notice, one is there. Okay, sorry. I'm so sorry. The number of matches is still the same. This should do. Yes. So I did it. I don't think like I have to explain too much in detail. I have to do what I have been told. So if the current number of teams is even, what we need to do is basically we need to calculate two things: the number of matches we played in this round and the number of teams that will like go into the next round, right? So for calculating the number of matches, if it's even, of course, every team will be paired with a random team. So the number of matches will be half of the total number of teams, right? And half teams, like 10 by 2 teams, go to the next round. The next condition or the second condition is when the number of teams are odd, we select one random team, like, and put it outside. Now we get even number of teams out of which we pair them and make them play the game, compete against each other. So basically, the number of matches played is n minus 1 by 2, but the number of teams that are going into the next round is like 1 plus n minus 1 divided by 2, which we can write in this fashion also, n plus 1 divided by 2, whole divided by 2, and just written the count of the matches count. Submit. That's done. Okay, so we'll move on to the next thing. Okay, let me show you. So as you know that I have been like reading one paper daily from this GitHub repo, which is System Design Resources by Interview Ready. I was doing video processing, and this will be my last video of this video processing series. I have done video transporting videos at scale. Uh, so we talked about like how YouTube works on this, on the transcoding of videos. Then we talked about how Facebook broadcasts live videos to millions of users all at once. And then third thing, like which we read yesterday, was Netflix video encoding with scalability, of course. And the one which we will be covering today is Netflix short-based encoding. Let's go. Okay, so optimize short-based encodes now streaming by Megha Manohara, Anush Murthy, Jandy Cock, Ionis Katsa Vonides, and Anne Allen. Okay, this was written like more than like 5.5 years ago. Bad picture quality, so blockiness, blurring, distorted faces, and objects can draw you out of that favorite TV show or movie you are watching on Netflix or any other streaming platforms. In many cases, low bandwidth networks or data caps prevents us from delivering the perfect picture to our clients. To address this, the Netflix video algorithms team has been working on more efficient compression algorithms that enable Netflix to deliver the same or better picture quality while using less bandwidth. Minus is basically the amount of data uh, that we can access, like the rate of data access we can have per unit time of this. When we use the term rate, it basically means per unit time. And if you want like an official definition of bandwidth, let's see. So it's the data transfer capacity, right? And bits per second, so BPS, it's like a rate, right? It's like a speed. That's the difference between like having mobile data versus having a Wi-Fi network. Both can get you like the same amount of data, but the rate at which you are getting the data is what matters. Okay. So bad picture quality, blockiness, blurring, distorted faces and objects can draw you out of that favorite TV show or movie you're watching on Netflix. In many cases, low bandwidth networks or data caps prevent us from delivering the perfect picture. To address this, the Netflix video algorithms team has been working on more efficient compression algorithms that enable Netflix to deliver the same or even better picture quality while using less bandwidth. And working together with other engineering teams at Netflix, we update our client applications and streaming infrastructure to support the new video streams and to ensure seamless playback on Netflix devices. Okay. So to improve our members' video quality, we developed and deployed per title encoding. So per title basically means, let's say, per title encode optimization. So we have spent years developing an approach called title encoding, where we run analysis on an individual title. Individual title basically means individual video, right? It could be a movie or it could be like an episode of a web series or a drama, right? Whatever it may be. So we run analysis on an individual title to determine the optimal encoding recipe based on its complexity. Imagine, imagine having a very involved action scenes, okay, that need more bits to encapsulate the information versus unchanging landscape scenes or animation that need less, okay. This allows us to deliver just more same or better experience while using less bandwidth, which will be particularly important in lower bandwidth countries as we expand to places where video viewing often happens on mobile networks, right, rather than Wi-Fi. Okay. So background, let's talk about background. So in traditional terrestrial cable or satellite TV, broadcasters have an or allocated bandwidth, and the programs are encoded such that the resulting video streams occupy the given fixed capacity. Statistical multiplexing is often employed by the broadcaster to efficiently distribute the bitrate among the simultaneous programs. However, the total accumulated bitrate across the programs should still fit within the limited capacity. In many cases, padding is even added using null packets to guarantee strict constant bitrate for the fixed channel, thus wasting precious data rate. Furthermore, with preset channel allocations, less popular programs or genres may be allocated lower bit rates and therefore worse quality than shows that are viewed by more people, right? With advantages of internet streaming, I won't read like much. Let's just read this paragraph and go back to our original paper. So the advantages of internet streaming, Netflix is not bound to pre-allocated channel constraint. Instead, we can deliver the best video quality stream to a member, no matter what the program or genre, tailored to the member's available bandwidth and being device capability. We pre-code the streams. Okay, before serving the video to the users, the subscribers, we pre-code it or pre-encode it rather, um, in various bit rates. So we can serve like different video encodes to people like, depending on the available bandwidth. So on the member's device, the Netflix client runs adaptive bit streaming algorithms, which instantaneously select the best encode to maximize the video quality while avoiding playback interruptions due to like rebuffers, right? Okay, so encoding with the best recipe is not a simple problem. Okay, for example, assuming a 1 Mbps or megabits per second bandwidth, should we right stream H dot 264 ABC at 480 pixel, 720 pixel or 1080 pixel with 480 pixel 1 Mbps will likely not exhibit encoding artifacts such as blocking or ring. But if the member is watching on a HD device, the unsampled video will not be sharp. On the other hand, if we encode a 1080 pixel, we send a high resolution video, but the bitrate may be too slow, such that most things will contain annoying encoding artifacts. So let's go back to our original paper. Mm, okay, there's a second paragraph here. So to improve our members' video quality, we developed and deployed per title encoding in 2015, followed by better mobile encodes for downloads a year later. Okay, followed by better mobile encodes for downloads a year later. Our next step was productizing a short-based encoding framework called Dynamic Optimizer, resulting in more granular optimizations within a video stream. In this article, we describe some of the implementation challenges we overcome in bringing this framework into our production pipeline and practical results on how it improves the video quality for our members. Mm, okay, let's Is again, so our next step was productizing a short-based encoding framework called Dynamic Optimizer, resulting in more granular optimizations within our video streams. So in this article, we discuss some of the implementation challenges we overcame in bringing this framework into our production pipeline and practical results and how it improves the video quality for our members. Implementing Dynamic Optimizer in production. As this described in more detail in this blog post. The dynamic optimizer analyzes an entire video over multiple quality. Okay. So basically analyzes a particular video or just tests a particular video over multiple video qualities and resolution points in order to obtain the optimal compression trajectory for an encode given an optimization objective. In particular, we utilize VMAF, um, the Netflix subjective video quality metric, but basically a video quality metric as an optimization objective. Since our goal is to generate streams at the best perceptual quality. The primary challenge we faced in implementing the dynamic optimizer framework in production was retrofitting. Okay, the primary challenge we faced in implementing the dynamic optimizer framework in our production pipeline was retrofitting our parallel encoding pipeline to process significantly more encode units, okay, simultaneously or concurrently. First, the analysis step of over the dynamic optimizer required encoding with different resolutions and qualities. Okay, the analysis step for the dynamic optimizer required encoding with different resolutions. Wait a minute, encoding with different resolution. What's the analysis step for the breed dynamic optimizer required encoding with different resolutions and quality, requiring an order of magnitude more complexity. Second, we transitioned from encoding video chunks of about few minutes long to video encodes on a per shot basis. Okay. First, we had video chunks of like few minutes long. If you have like a 3 hour movie, video, then we would divide it into chunks, each of a few minutes, each a few minutes long. But now we do that like video encode on a per shot basis. For example, in the original system, a 1 hour episode of Stranger Things results in 23-minute chunks. So 20 into 3, 60 minutes, right? With short-based encoding with an average shot length of 4 seconds, just 4 seconds. The same episode requires processing of 900 chunks or shots, assuming each chunk corresponds to a shot, figure 1b. Okay, the new framework increased the number of chunks by more than two orders of magnitude per encode per title. This increase exposed system bottlenecks related to the number of messages passed between computer instances. Several engineering innovations were performed to address this limitation, and we discussed two of them here, collation and checkpoints. Okay, while we could have improved the core messaging system, okay, to handle such an increase in message volume, it was not the most feasible and expedient solution at that time. Okay, let's see, let's hear that again. While we could have improved the core messaging system to handle such an increase in the message volume, right, between the different encodes or chunks, it is not the most feasible and expedient solution at the time. What do you know, expedient? Related to expenses? I probably think so. Okay, convenient or helpful for a purpose, but possibly not completely honest or moral. Okay. Okay, we instead adapted our pipeline by introducing collation. Okay, let's see and understand this diagram. So we have like ABC, I don't know what they are. A is like representation of a video timeline, collection of shorts in the chunks, maybe collection and joining together of different shots into chunks. Representation of a video timeline, the dashed vertical black lines Okay, so represent short boundaries. Okay, so we have different shots. Got it. But like they are not of uniform length, which you can see clearly in the diagram A. Then for B, we have like one shot in one chunk. And what is that? Each shot is assigned a chunk. Okay, each shot is assigned a chunk. Cool, cool. And thirdly, we have like collate shots into a chunk. Okay, so we can accumulate integer a fixed number of shots into a chunk, the target chunk duration. So basically, for a whole video, we could divide it into multiple shots, each having like different time frames. And after that, like after dividing the video into different chunks, we want to join them or collect them back into chunks. But we want the chunks to be of equal length. So in doing so, we could every chunk could have different number of shots. For example, if you see like figure C, in the first chunk we have one, two, three, four shots, whereas in the second we have like three shots, and all of them are of different lengths. You can see that clearly. So in collation, what we do? Let's see. So in collation, we collect shots together. Collect means collect together, maybe. Let's say. Collate. Okay, let's see. To collect information from different places in order to put them together, examine and compare. Kind of we get it, like what it actually means, right? Let's get back. So in collation, we collate shots together so that a set of consecutive shots make up a chunk. Now, given that we have flexibility in how such collation occurs, we can group an integer number of shots together so that we can produce approximately the same 3-minute chunk duration that we produced initially under the chunk-based encode model, figure 1C. So these chunks could be configured to be approximately the same size, yes, which helps with resource allocation. For instances previously tuned for encoding of chunks a few minutes long, within each chunk, the compute instance independently encodes each of the shots with its own set of defined parameters. So, an encode request with a chunk to be encoded, which have like different, like each chunk will have different number of shots, and each shot will be or maybe of different lengths. So, lines correspond to a shot to be encoded serially, one after the another. Very important. Uh, we can like encode the chunks parallelly, but for encoding the shots together we have to do it serially. So one encode instance runs through the first three shots in green, okay, and the work is lost at the fourth shot. Okay, the same unfinished encode request is picked by different encode instance, which first checks if there are any checkpoints. Okay, checkpoints are very important. Like even while downloading something, so you may have noticed like while downloading something, and if the network connection goes up for a few seconds, and it gets restored after some time, we can start downloading from where we left off. So that's the power of checkpoints, which is very useful. This is the same unfinished encode request is picked up by a different encode instance, like EC2 instance, whatever be the computing instance. So which first checks if there are any checkpoints or shots in the cloud, and it so starts at the first shot without a checkpoint. So it reduces a lot of like time. Collating independently encoded shots within a chunk led to an additional system improvement we call checkpoints. Previously, if we lost a compute instance because we had borrowed it, right? and it was suddenly needed for higher priority tasks. We re-encoded the entire chunk. In the case of shorts, each shot is independently encoded. Once a shot is completed, it does not need to be re-encoded if the instance is lost while encoding the rest of the chunk. Cool. So we created a system of checkpoints to ensure that each encoded shot and associated metadata are stored immediately after completion. We created a system of checkpoints to ensure that each encoded shot, okay, and associated metadata are stored immediately after completion. Now, if the same chunk is retried on another compute instance, encoding does not have to start all over again from the scratch, but from the shot where it left off. Bring down the computational savings. Compression performance. In December 2016, we introduced ABC High Mobile and BB9 mobile encodes for downloads. For these mobile encodes, several changes led to improved compression performance over per title encodes, including longer GOPs, flexible encoder settings, and per chunk optimization. These streams serve as our high quality baseline for H.2640VC and BP9 encoding with with traditional rate control settings. The graph below, figure 3, demonstrates how the combination of dynamic optimization with short-based encoding further improves the compression efficiency. We plot the bitrate, VMAF curves of a new optimized encodes referred to as P9, VP9 opt and AVC high opt compared to per chunk encodes for downloads, VP9 mobile and AVC high mobile versus like per title encodes for streaming ABC main. To construct this graph, we took a sample of 1,000 of titles from our catalog. For each bitrate X on the horizontal axis, and for each title, we selected the highest quality encode. Okay, as expressed by a VMAF score with bitrate less than X, with an averaged VMAF values across all the titles for the given X, which were 1 point for each curve in the following figure. Sweeping overall bitrate values X, this resulted in 5 curves corresponding to the 5 types of encodes discussed above. Assuming stable network connections conditions, this is the average VMAP quality you will receive on a Netflix service as at that particular video bandwidth. So on the x-axis we have like bitrate, which is a kind of red bitrate. So the amount of data in kilobits per second, right? So compression efficiency of per title, per chunk, and newly optimized encodes in the VMAP. So let's illustrate the reduction in bitrate equivalent quality by drawing a horizontal line at VMAP 80. Good quality, which gives us the following bitrates. Okay, so bitrate at VMAP 80. Let's see. So ABC main is the highest, which is 10, 12, 60 kbps, kilobits per second. ABC high mobile is like about half, 720 kbps. And VP9 mobile, 580 kbps. AVC high opt is 600 kbps. And lowest we have like VP9 opt, 400 kbps. You can see that compared to per title encoding with the ABC main, the optimized encodes require less than half of the bits, maybe like 1/3 of the number of bits to achieve the same quality. With VP9 opt, we can stream the same quality at less than 1/3 of the bits used by ABC main. Compared to ABC High Mobile and VP9 Mobile, we save 17 and 30% respectively. We also examine how visual quality is impacted given the same bandwidth. We also examine how visual quality is impacted given the same bandwidth. For example, an average cellular connection bandwidth of 250 kbps results in the average VMAP values shown in the table below. The optimized encodes provide noticeably better video quality than ABC main. So ABC main average VMAP at 250 pixel, 52, ABC high mobile 57, AV9 mobile 63, ABC high opt 66, and DV9 opt with the highest score of 73. So to illustrate the difference in visual quality, the example below shows a frame from a chef's table episode taken from different encodes with approximately 250 kilobits per second bitrate. Immediately noticeable is the increased quality in textures, like more visible are the details right in the picture, like bricks, trees, rocks, water, etc. A visually noticeable difference observed within ABC main figure 4a, ABC main at 250 kbps, VMAP is 58, and ABC high opt, figure 4b, VMAP 73, the the VP9 opt frame, figure 4c, VMAP 79 looks sharpest. Yes. So in the following example, we show a detail of the opening scene of 13 Reasons Why at approximately 250 kbps. For ABC main figure 5a, the text at the top is hardly legible, deserving a VMAP value of 60. For ABC high opt figure 5b, we see a large jump in quality to a VMAP of like value 74. For B9, VP9 opt, VP9 opt figure 5c, the text images become crisp, crisp. And we get another noticeable increase in quality, which is also reflected in the VMAP score of 81. Testing optimized encodes in the field. So in the previous section, we illustrated that optimized encodes offer significantly higher compression efficiency than per title encodes. So in the previous section, we illustrated that optimized encodes offer significantly higher compression efficiency than per title encodes, right? Leading to a high quality at a comparable bitrate or lower bitrate at same quality. The question remains whether this translates into an improved. The question remains whether this translates into an improved experience for our members. Before deploying any new encoding algorithm into production, we thoroughly validate playability of the strings using ABC testing on different platforms and devices. A/B testing provides us with. Before deploying any new encoding algorithm into production, we thoroughly validate playing of those streams using A/B testing on different platforms and different devices. A/B testing provides us with a controlled way to compare the quality of experience QoE of a treatment sale or that is a new encodes to the control cell that is the existing experience. This will compare our new encodes a quality experience with that of the existing experience. We ran A/B tests on a wide range of devices and titles to compare our optimized encodes against the existing ABC mainstreaming experience. This has also allowed us to find Or this also allowed us to fine-tune our encoding algorithms and adaptive streaming engine for different platforms. We assessed the impact of optimized encodes on different QoEs, basically quality of experience matrix. Based on the results of A/B testing, we expect the following improvements to our viewers and members' viewing experience. For members with low bandwidth connections, we will deliver higher quality video at the same or even lower bit rate. Okay. For members with high bandwidth connections, will offer the same great quality at lower bit rate. Many members will experience less rebuffers and quality drops when there is a drastic reduction in the network throughput. Devices that support VV9 streams will benefit from even higher video quality input. In addition, many of our members have a data cap on their cellular phones. With the new optimized encores, these members can now stream more hours of Netflix at the same or better quality using the same amount of data. Now, the members can stream more hours of Netflix at the same data and at a better or same quality. The optimized encores are also available for offline downloads feature. For downloadable titles, our members can watch noticeably high quality video for the same storage. Re-encoding and then the device support. Over the last few months, we have generated AVC high opt encodes for our entire Netflix catalog. If we use like V9, GP9. What is the full name like GP9 opt? Okay. You can currently enjoy these optimized streams when watching Netflix on iOS, Android, PS4, and Xbox One. VP9 opt streams can have, have been made available for VPN opt streams have been made available for a selection of popular content and can be streamed on certain Android devices. We are actively testing these new streams on other devices and browsers. Whenever you're Whenever you're watching Chef's Table on a smart TV with the fastest broadband connection, or Jessica Jones on a mobile device with a choppy cell network, Netflix is committed to delivering the best picture quality possible. The launch of the new optimized encodes is an excellent example of combining innovative research and Netflix is committed to delivering the best picture quality possible. The launch of the new optimized encode is an excellent example of combining innovative research, effective cross-chain engineering, and data-driven deployment to build and bring a better experience to our members. It was a good read. I liked it. A few claps and a comment. Yes. Okay, next we'll move on to Hero. Sometimes all I think about is you. Late nights in the middle of the moon. Heat waves been picking me up. Can make you happier now. Sometimes all I think about is you. And the middle, heat waves been picking me up. Can make you. Mhm. 44 minutes हो गया चला ये देख लेते हैं Yes. Okay. I'm watching at 1.5, I guess. Yeah. I think I have to end this stream because the laptop is getting like too hot. So that's all for now. Good night.